Throughout history, groundbreaking experiments have fundamentally transformed our understanding of the physical world. These pivotal moments didn't just advance science, they revolutionized how we perceive reality itself. From the motion of falling objects to the bizarre behavior of quantum particles, each experiment challenged existing beliefs and opened new frontiers of knowledge. Let's explore the experiments that changed everything. Around 1589 to 1592, Galileo Galilei conducted one of the most iconic experiments in physics history. He dropped objects of different masses from a great height to test a long-held assumption. For nearly 2,000 years, people believed Aristotle's claim that heavier objects fall faster than lighter ones. But Galileo's experiment proved otherwise. Both objects hit the ground at essentially the same time, regardless of their mass. This simple yet elegant demonstration shattered Aristotelian physics and laid the groundwork for our modern understanding of gravity and motion. In 1666, Isaac Newton performed a deceptively simple experiment that revolutionized our understanding of light. He took a beam of white sunlight and passed it through a glass prism. Instead of remaining white, the light spread out into a beautiful spectrum of colors: red, orange, yellow, green, blue, indigo, and violet. This proved that white light isn't pure or simple, but actually composed of multiple colors blended together. Newton's discovery established the science of optics and transformed how we understand light, color, and vision itself. Between 1797 and 1798, Henry Cavendish conducted an extraordinarily precise experiment using a delicate apparatus called a torsion balance. He measured the tiny gravitational attraction between lead spheres of known mass. This allowed him to determine the value of the gravitational constant. Commonly written as capital G. With this constant, Cavendish calculated something remarkable: the actual mass and density of the entire Earth. It was the first time humanity could weigh our own planet, making this one of the most important measurements in scientific history. In 1801, Thomas Young performed an experiment that would settle a centuries-old debate about the nature of light. He passed light through two narrow, closely spaced slits and observed the pattern that formed on a screen behind them. Instead of two bright lines, he saw alternating bright and dark bands, an interference pattern. This pattern could only be explained if light behaved as a wave, with waves from the two slits either reinforcing or canceling each other. Young's experiment decisively established the wave theory of light, fundamentally changing physics. In 1887, Albert Michelson and Edward Morley conducted what's often called the most famous failed experiment in physics. Scientists at the time believed that light waves must travel through an invisible medium called the luminiferous aether, just as sound waves travel through air. The experiment used an extremely sensitive device called an interferometer to detect Earth's motion through this supposed aether. But they found nothing. No matter how they oriented their apparatus, they detected no aether whatsoever. This null result disproved the existence of the aether and paved the way for Einstein's revolutionary theory of relativity. In 1909, Robert Millikan performed an ingenious experiment to measure one of nature's most fundamental constants. He suspended tiny oil droplets in an electric field and carefully measured how the field affected their motion. By balancing electric force against gravity, he could determine the electric charge on each droplet. Millikan discovered something profound: electric charge always came in exact multiples of a basic unit. This proved that charge is quantized, existing only in discrete packets, and allowed him to measure the elementary charge with remarkable precision. This fundamental constant is crucial to all of modern physics and chemistry. Between 1909 and 1911, Ernest Rutherford and his team fired alpha particles, positively charged helium nuclei, at an extremely thin sheet of gold foil. According to the prevailing atomic model, these particles should have passed straight through with minimal deflection. Most did, but astonishingly, some bounced back at large angles. Rutherford famously said it was like firing artillery shells at tissue paper and having them bounce back at you. This shocking result revealed that atoms aren't uniform puddings of matter, but instead have a tiny, dense, positively charged nucleus at their center. This discovery completely revolutionized atomic physics. In 1922, Otto Stern and Walther Gerlach sent a beam of silver atoms through a non-uniform magnetic field. Classical physics predicted that the atoms should be deflected by varying amounts, creating a continuous spread on the detector. Instead, they observed something bizarre. The beam split into only two distinct spots. This demonstrated that a property called quantum spin can only take specific, discrete values. The atoms were either spin up or spin down, with nothing in between. This experiment provided direct evidence for spatial quantization and became a cornerstone of quantum mechanics. In 1927, Clinton Davisson and Lester-Germer fired a beam of electrons at a nickel crystal and observed how they scattered. If electrons were simply particles, they should have bounced off in all directions. Instead, the electrons created a diffraction pattern, alternating regions of high and low intensity, just like waves do. This was direct experimental confirmation of Louis de Broglie's radical hypothesis that matter particles can behave as waves. The experiment proved wave-particle duality, showing that the quantum world is far stranger than anyone imagined. This discovery was absolutely fundamental to quantum mechanics. Between 1956 and 1957, physicist Qin-Shiung Wu conducted an experiment that shook the foundations of physics. She cooled cobalt-60 atoms to temperatures near absolute zero and observed their radioactive beta decay in a magnetic field. Physicists had long believed in parity conservation, the idea that physical laws are the same whether viewed directly or in a mirror. But Wu's experiment showed that beta particles were emitted preferentially in one direction. This proved that the weak nuclear force violates parity symmetry. Nature, it turns out, can tell left from right. This groundbreaking discovery earned her colleagues the Nobel Prize and transformed our understanding of fundamental forces. From Galileo's falling objects to Wu's parity violation, these experiments share something profound in common. Each one challenged what we thought we knew and revealed deeper truths about reality. They showed us that light is made of colors, that atoms have nuclei, that particles can be waves, and that nature itself can distinguish between left and right. These weren't just incremental advances, they were revolutionary transformations in human understanding. Together, they form the foundation of modern physics and remind us that careful observation and clever experimentation can unlock the deepest secrets of the universe.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.